Hello everyone. Let me give you a few tips about this upcoming seminar. So first, how do I start? Let us discuss the questions that I have given to you. So let us discuss those questions first. Then I'll give you some tips. So first is, what is the resolving power of a telescope? So the telescope, in telescope there are two objects far away in the sky. So the resolving power is determined by 1 by delta theta. So delta theta is the smallest angle that can be. So this is smallest. It is a minimum angle that can be resolved by the telescope. So if the two objects subtend a smaller angle than delta theta at the telescope, then the telescope will not be able to differentiate between the two objects. So any angle which is greater than delta theta, the telescope will be able to resolve. So delta theta is the minimum angle that can be resolved by the telescope. So the resolving power of the telescope is given by 1 by delta theta. And it has an expression. So it is d by 1.22 by lambda. So we need not worry how this expression came. So what is derivation? Derivation is not required. This expression is good enough. So what is d? D is the aperture size. So larger the aperture size of the telescope, the greater will be its resolving power. And lambda is the wavelength of light that is being captured by the telescope. So that's why we say larger the value of d, the aperture, greater will be the resolving power. So you can just go to the internet and have a look. I'm just telling you briefly, and you have to know briefly also. You don't have to know in great details. Then there is the electromagnetic spectrum. So electromagnetic spectrum, it is on the high energy side we have gamma rays, then X-rays, and so on and so forth. Then we have the visible region, we have infrared, and then we have the larger wavelengths. Okay. So what is the wavelength range of visible region? So these are the questions the audience may ask. What is the visible range? What is the wavelength range of visible spectrum? What is the wavelength range of infrared spectrum? Because since we are working with an infrared telescope, we are interested what is the infrared spectrum, what is the wavelength range. So from this to this, that is the range. And the telescope was delivered to its final destination by a rocket. So a rocket uses fuel. So what kind of fuel is that? It uses liquid oxygen as an oxidizer. So what is the fuel that burns and gives the energy? Just check the internet. There are many kinds of fuel, but one kind of fuel is very commonly used. What is that fuel? And in the mirror of JWST, beryllium is used. So why beryllium? So there may be some special properties of beryllium which are important and which are helpful for the mirror working deep into the mirror, which is placed deep into the screen. So just check the internet. What kind of property of beryllium can be useful for this kind of mirror? Then, why is this telescope so far away from the Earth? We cannot keep it very close to the Earth because there are other sources of infrared spectrum, so that will spoil the data. So we want clean data, so we have to take it far off from the Earth. But why did we take it so far off, than 1.5 million kilometers? So why can't we place it slightly nearer, or something like 500,000 or something like that? So that has to do with L1, L2, so I discussed the 5 Lagrange points. So those are points which are fixed with respect to the Earth. You can't place it anywhere. So you have to place it in one of those 5 Lagrange points, so that it is at a constant distance with respect to the Earth. So L2 is a suitable position. That's why it is so far off from the Earth. So we don't want this telescope to orbit the Earth, because that way we are not interested in any data coming from the Earth. Whatever data is there, it will be coming from outer space. So it has to move away from the Earth. And why L1, L2, and why this Lagrange points is important, let us discuss. So just go through whatever I had said, nothing more. Everything what you have to know, you have to know a little, superficially, but you have to know a little. Hubble's law. What is Hubble's law? Cosmology Hubble's law is an important law, which, like, with respect to the Earth, all the galaxies are moving away. How are they moving away? The velocity at which the galaxies are moving away is proportional to the distance between the Earth or the galaxy. So this proportionality constant is called Hubble's constant. So greater the distance of the galaxy, greater will be its velocity. So the Hubble's constant is a constant. So its value is around. So V is proportional to D. So V is equal to some Hubble is equal to Hubble's constant into D. The Hubble's constant is a value. So it has to be dimensionally correct. So it should have the dimension of velocity by distance. So its value is around 70 kilometer per second per megaparsec. Megaparsec is a unit of distance. So what does it tell us? That if a galaxy is 1 megaparsec away from the Earth, then the velocity with which it's moving away or receding away from the Earth is 70 kilometer per second. If the galaxy is even further away, which is more than 1 megaparsec, then its velocity with which it is receding away will become even greater. So this is actually about the expanding universe. So how fast is the universe expanding? That is given by the Hubble's constant. Right. So Hubble's constant, whatever the Hubble's constant is, that is the rate of expansion of the universe. So the expansion of the universe rate is 70 km per second per megaparsec. So the universe is like, suppose, a membrane. So the membrane is stretching. So the distance between the points is also increasing. At what rate it is increasing? So it's not so. The further the point is, the increase is more. That's what it says. If the distance is 1 megaparsec, then they are moving away with respect to one another at 70 km per second. But if the point is, say, further away, then it is moving away at an even greater distance, at a greater velocity. So Hubble's constant actually gives you the rate of expanding universe. What is redshift in physics? Redshift in physics is like Doppler effect. When the source is moving away from the observer, what we observe is the frequency is decreased or the wavelength is increased. So that is called redshift. The increase of wavelength means from higher frequency I am going to lower frequency. So from ultraviolet I am going to red. So that's why it's called a redshift. If the wavelength increases, then it is called redshift. And cosmological redshift is increase in wavelength due to expanding universe. So since the universe is expanding, if something was, say, a gamma ray has a very short wavelength. Now after so many years, if in the early universe some gamma ray was emitted, that gamma ray now is now not gamma ray anymore, because its wavelength has increased. It may now be an infrared. Okay, so that is the cosmological redshift. So The wavelength of the gamma ray has increased, and now it has become the wavelength corresponding to infrared. So that is called cosmological redshift. So dark age of early universe. So what is the dark age of early universe? So when universe began with a big bang, it was so hot that everything was in a state of plasma, like everything was ionized. There was no matter, neutral matter. So we had nuclei and we had electrons, which was the soup, and you know this was a soup of charged particles. So when electromagnetic wave goes through, electromagnetic wave means electric field and magnetic field. If it goes through charged particles, then the charged particles get disturbed. So that means this electromagnetic wave or light, as we say, was constantly getting scattered of these charged particles. So it was like a very, so the early universe was almost opaque. There was so much of scattering around because light was getting scattered of these scattering centers, electrons and nuclei, but it was almost opaque. Then as the universe expanded and it cooled, then what we had is, we had neutral atoms like hydrogen. Then hydrogen started forming. And as hydrogen started forming, this matter and electromagnetic radiation decoupled. So this scattering stopped because now we had neutral atoms. So the charged particles were not floating around that much. Right? So we had many neutral atoms. So that radiation, this microwave, belongs to the microwave spectrum. That is, it has a large wavelength, even greater than infrared. And that is not visible to eye. Is it not microwave? So that was CMB, cosmic microwave background radiation. That is when your matter and radiation decoupled. And we have CMB. And CMB is microwave, so universe became dark. And from that dark universe, so what happened is that suddenly stars started appearing. It's just like in a very dark place, suddenly bulbs started lighting up. So it was like that. It was very dark, okay, and suddenly star formation, galaxy formation started taking place. So we had early universe like a very hot soup where light was always scattering around. Then we had the dark age when we had neutral hydrogen and we had microwave background radiation. So we had dark universe, and then suddenly stars started appearing and the universe started lighting up. So these things you just have to know a little bit. I'm just telling you, if you want, you can check the internet. And what is a supermassive black hole and what is a black hole? Black hole, you know, is it does not allow even light to escape, and black holes are generally formed when certain kind of stars die. Then we have black holes. So a black hole can contain 30 times, 40 times, or 50 times the mass of Sun. That is a typical black hole. But there are another kind of black hole which may not have been formed due to death of a star. So such black holes can contain, say, 10 to the power 6 times, 10 to the power 8 times the mass of the Sun. We still don't know how these black holes originated. We know this black hole, we don't know about supermassive black holes. They did not originate from stars. Okay? Sorry. They did not originate from stars. So that is the difference between black hole and supermassive black hole. You can just check the internet also. That is all I have to say. And one more thing is, when you are giving a seminar, don't just read from whatever in the slide. Okay? What are the main things like Hubble's constant, redshift, and then tell in your own words to your audience what you have to say. Don't just read and stop. Just read everything and then we go to the next slide. This is not a good practice. So we have to just point out the main things and tell in your own words the audience what to think. And always remember, whatever there is on the slide, you have to know a little bit about it. Just you copied something and put it on the slide, it's not a good thing. You may not know a lot, I understand, but just superficially, if you know a little, that is enough. Like when you use abbreviations like NIR cam. What is NIR cam? It is near infrared camera. So those things you have to know. You just write NIR cam, and if somebody asks what is NIR cam, you don't know. So that should not be there. Or what is nebula? Okay, you use the word nebula, but you don't understand. But if you don't ask somebody else what is nebula, you don't know. So everything, whatever is there on the slide, little bit you have to know. Just a little bit. That is it. We are not expecting you know a lot and you have to work out everything. Everything should be short. Like if you ask somebody short, they should be short answers, but clear short answers. And practice a little. At least practice once or twice, so that you can time. Try to finish it within 25 minutes. And speak slowly. Don't speak very fast. Speak slowly and time it, and so that you will know what to say and what not to say, so that you can finish within 25 minutes. Audience will ask questions in audience ones, that's fine, we'll take into account all the things. But in your practice session, try to finish it within mock practice sessions. You can mock sessions. You can finish. You can try to finish it in 25 minutes. So that will be good. Okay. And so practice once or twice, then you will get a handle of the. You will understand what to say and what not to say, how much to say, how much not to say. Okay. And that will be all. Thank you.